Well, good morning, students. Hope you had a happy Thanksgiving. And we are, for this week, meeting virtually once more. So, today's lesson, I'm going to try to move us another step in our understanding of circuitry. We have covered resistance, voltage, amperage. We've looked at the difference between a parallel and a series circuit. And last week we looked at how we could even make a homemade battery out of things you've got right in the house, some vinegar, salt, and that zinc-coated plated nickels and copper pennies with a electrolyte in between. So hopefully you got a chance to try that out. I seriously was impressed seeing that we could get a voltage just by making things from here around the house. There are probably three more components that I would like to run a lesson through for you to have exposure to what we use in modern circuitry. That they would be a capacitor, a transformer, and lastly is what's called an integrated circuit. Today we're just going to look at a capacitor. And then in the future, if we do some more of these, we will take a look at the other two. Transformers, I think, are an incredible technology. And then for technology class here and your continued investigation into computers and the working of computers, we got to at least take some time to look at the integrated circuit. And without the integrated circuit, we would not have computers as we have them today. But I'm going to save both of those for a future lesson. And so for today, what I want to talk to you about are capacitors. A capacitor is a small, sometimes it looks like a barrel. In fact, I had one here. I might have to go find one and edit this to show you. Sometimes they look like a little barrel with two little terminals coming out the end. Other times they'll look like an orange or amber colored little wafer that again is connected with two terminals. We use a property within electromagnetism that I think would best be understood with an illustration towards static electricity. Now you know what static electricity is. When you are pulling clothes out of the dryer, right, and they stick together, that's because there is a attracting force between positive protons and the negative buildup of electrons on a certain type of cloth or fabric. And so you'll have one piece of cloth, like a sock, a wool, maybe a wool sock, will stick to another fabric, and it just sticks there, it just stays there. You could also try an experiment where you take a balloon and blow it up and then rub it on your hair, and what will happen is you'll begin to strip electrons off of the hair on your head and transfer that to the surface of the balloon so that the balloon now becomes negatively charged. Now, whether we're talking about a balloon or if we're talking about laundry that comes out of the dryer, what we're referring to is a buildup of electrons. Static electricity, and if you've ever been shocked, if you're pulling clothes apart, you can feel that voltage on your fingertips when you're pulling the clothes apart. Or if you've ever maybe drug your feet across a carpeting with some wool socks and stuck your finger on your brother or your sister, and you can give them a shock, it's because static electricity is the buildup of electrons on a surface that can be quickly discharged. A capacitor takes advantage of this physical property of electricity by storing it in a small container, that little barrel-shaped unit that makes up a large capacitor, or sometimes those small wafer-sized ones. What they're doing is they are actually storing up electricity that can be discharged according to the need, and sometimes discharged even very quickly. When we're looking at a capacitor, we want to understand what's going on the inside. Now I don't have one here. I really should try to find one. But what I do have is, as an illustration, is fly paper. Now, fly paper is going to work for this illustration, that we would understand what's going on inside of a capacitor. But this is what basically some capacitors look like. This is about the size that they look like. And if I were to unroll this, just as if I were to unroll a capacitor, what you will find is that inside is a material that's very tightly, see if I can get a picture of it, tightly wound together. There. Can you see the windings and how they go one around the other, just like that? Now, in this case, with fly paper, the material on the inside is that sticky tape, so it can attract a fly and get stuck to it. But inside of a capacitor, what you have are two sheets of metal, one that's going to be positive and then one that's going to be negative. And you might remember from our last video, we call the positive side the cathode, and we call the negative side the anode. So the cathode and the anode side, basically two sheets of metal, and in between those sheets of metal, what you have is a piece of paper. So a sheet of paper that goes in between, or not a sheet, necessarily a sheet of paper, but a substance that doesn't allow the two sheets of metal to touch one another. Let me see if I can, I'm going to get some paper and show you. Take a look. Okay, we are going to take a look at how a capacitor is structured on the inside. And in order to do that, we need some tin foil and some paper. And what I'm going to do, I'm just going to get the right dimensions here of the aluminum foil. And I could probably just tear this if I'm careful. Do it just like that. That'll work. And same along this side. Right along the edge. Good. All right. Now, inside of a capacitor, you will find two pieces of metal separated by something called a dielectric. And what I'm going to do is I'm going to cut this in half so that I get two pieces of metal with one sheet of paper that's approximately the same width apart. All right. Good. So here are my two pieces of metal, and here is the separator in between the two. And what we're going to do now is is show you how these are set up. Excuse me, set up on the inside. If you were to imagine that you were to take just this one side and charge it up by connecting it to a battery, this side over here, if it were to touch, would discharge the current that's stored up, that static electricity that builds up on the positive side. So in order to keep that from happening, what you have to do is put something that will allow the interaction between the two, but will separate them so that they won't actually touch one another. One way that you could envision this same type of interaction is by using a magnet. I've got a magnet right here, and as you can see, it is oppositely charged, so positive side and negative side. And if I were to put something in between, well, sure enough, it still conducts. In fact, if I can pull it all the way through to the end, you will see there the two are still able to interact even though they are separated by this dielectric material that's on the inside. And that's the same thing that's going to happen but instead of the magnets, we're going to have one of these be negatively charged with extra electrons and one of them be positively charged like this. So instead of magnets, we're talking about electrical current, and these are going to carry the same voltage as what you'll have in your battery. Now, as you look at this, you might think, well, this is kind of bulky. I've never seen anything this large inside of my computer. And that's because engineers have found a very clever way of making this much, much smaller. To show you that, I need to present to you something that my wife baked here for Thanksgiving, and that's this pumpkin roll. So if you've ever seen, or if you've ever had pumpkin roll, or those little, you will see that there is one side right here that's coiled up, and I don't know why I'm using this. I should probably be using this instead. One side that's coiled up, and the other side has this material that doesn't let it touch. It works. It works pretty good. In fact, very good. So this design here is the same that those clever engineers have figured out to miniature the size of a capacitor. And so I'm going to demonstrate that to you now. So remember, one of these is negatively charged, and as the electrons build up on one side, they push away the electrons on the other because like charges repel one another, and in between is this material called a dielectric. And so it gets sandwiched up together like this, and then what happens inside of a capacitor is it's rolled very tightly, just like you have on the pumpkin roll. And now you are able to have something, and I got a little wonky here, a little crooked, but now you're able to have something that is going to be still containing the same amount of charge as it was before, except taking up much less space. So a capacitor, if you were to look onto the inside of any small barrel-shaped capacitor, you will find something that looks very similar to this. And then on the inside, what you would have is a terminal coming off one end that's positively or negatively charged, and then the other one here is where the other terminal is going to touch, so that you've got a terminal on one side that's then coiling those electrons all the way around, and then a terminal on the other side. The two ways that you can increase the capacitance, and I'm going to demonstrate this in the simulation, is by increasing the surface area. So the larger the surface area that's here, the larger measure you're going to get for capacitance. And the second way that you can increase capacitance is by closing up the distance between the two metals. So the shorter the distance, the closer they are towards one another, the higher the capacitance. And then the further away that they are from one another, the lower the capacitance. Okay. So there you see, inside of a capacitor, you have those two sheets of metal that are then rolled up like a pumpkin roll, or a Little Debbie, or what are those called again? Swiss. You ever see those little chocolate candies that are rolled up? Very exactly similar to that. And that all of the electrons move to one side and thereby become charged. And as all those negative static forces occur on the one side, what they do is they repel, because negative repels negative. Like charges are not attracted to one another, and instead you build up a potential difference or a voltage, but it's not released because it has that dielectric material insulating between it. It's close enough that it's able to still be attracted and influence, but not enough to discharge it. Now we use capacitors to flatten out what is some variance in voltage versus current. So when the amperage becomes a little bit misaligned from the voltage, a capacitor will bring that back in line. Additionally, capacitor will be able to be charged up and to provide continuous current. So in a component where you're changing AC into DC, so alternating current into direct current, we use something called a rectifier, and a rectifier will sometimes produce sharp stops or spikes within the current. But if you added a capacitor to the circuit, what that will do will be to help smooth out that current. Capacitors are used in every electronic device that you see. If you were to talk to your parents, I don't think any of you necessarily remember this, but when I was your age, we had something called disposable cameras. This is before everybody had a camera in their pocket. And a disposable camera you could buy at Walmart, you could shoot 24 pictures and then throw it away. But many of these cameras, they came with a built-in flash. However, you couldn't take too many pictures at once because the flash wouldn't work any longer. The flash operated off of a capacitor. And so you would have a battery that was already inside of that camera. But as you took a picture, you would hear this high-pitched ringing sound going doo. It would be increasing like that. Even some flash bulbs for some DSLR cameras that use lenses, those flash bulbs also work off of a capacitor, because what they have to do is they have to discharge all of that electricity into a bright flash immediately. And that's what a capacitor does. It will carry the same voltage as what you will find with a battery, but it will be able to be discharged almost immediately. I want to just lastly leave you with a word of caution here to make sure that you're very careful when looking into any electrical devices or circuit boards, because a capacitor can actually do you great harm. There's a lot of voltage. In fact, the same voltage is stored up in a battery can be discharged immediately. And one time as a kid, I was taking apart one of those disposable cameras, and without knowing it, I touched both ends of the of the capacitor, and it gave me quite a nasty shock. So capacitors are just like batteries in that they provide electricity, but they're not conveying that electricity through any chemical means. It's a different potential voltage than what you find in a battery, but it stores electricity. So when you take a capacitor and you hook it up to a battery, what will happen is the current from that battery will build up across that dielectric so that it's ready to be discharged when you need it. Last thing I want to do is show you here with a simulation how a capacitor can be increased in terms of its, we measure a capacitance in something called farads. Generally it's called microfarads. The simulation I'm going to show you is going to refer to it in picofarads because it's using such a very small voltage. But I'll have you take a look at that right now. Okay, here is the simulation, and this link will be available for you there on Schoology to see. And I want to point out to you a couple of things here. So you have the battery over on this side. Up here, we're gonna click top plate charge and stored energy so that we see all those values increasing. And then right here we have our two sheets of metal that you saw in the demonstration I made as the aluminum foil. And what I want you to see is that as we increase the battery voltage, we're going to go straight up to 1.5 volts. You'll notice that the charges all go up, only a certain amount. Now the P in front of the F here stands for picofarads. So the capacitance here would be 9/100ths of a picofarad. So this is not a lot, and you'll notice part of the reason is because these two plates are pretty far apart from one another. If we were to disconnect it from the battery, you will see here we now have contained our current, and it still stays because it's just like we saw with the sock and the dryer. That static electricity is still there. So I'm gonna connect it back up once more, and now I'm going to show you how we will increase the capacitance right now. In fact, we're going to see the two different ways in which it will increase. One has to do with what we see here called plate area. So the area as it increases will increase the capacitance, and then the second here has to do with the distance the two plates are from one another. So watch what happens as I move the two plates closer to each other. Now they're only 4 millimeters away, and here we have more than doubled our capacitance. I'm going to go all the way that it allows me to go, a full just 2 millimeters away, and now more than 4 times the capacitance that was there before. So as you can see, as we move those two layers closer to one another, what you will find is that the capacitance increases. The second way that it will increase is by increasing the plate area. So as I move this slider and make it larger, you will see as well that our capacitance increases all the more. And what if we do both? Let's move them close together, and my goodness, look at these values have increased. These values have increased so much now that they're that much closer to one another. The last thing I want to show you again is that as we disconnect this from the battery, the charge remains. So a capacitor will hold its charge just like a battery being charged up by the battery, but it won't discharge until these two wires are connected with one another. We can even see this and measure it with the voltmeter. And if we bring these over to get a reading, what you will see is that reading is the same as the battery, except when they're disconnected. I gotta put them back over here, and there, once more, you'll see 1.5 volts here, the same voltage as what we have in the battery. So this is just a handy little illustration that shows you the two ways, I'll reset it here, two ways of increasing the capacitance of a capacitor, and that would be by decreasing the distance between the two sheets and by increasing the area. Well, that is one more component in our study of circuitry here. You now have got exposure to circuits, resistors, amperage, voltage, batteries, and now capacitors as well. I'm going to have a couple of questions that you could work through. I'd like you to be able to identify the positive side of a capacitor and the negative side of a capacitor. Those are additionally the same names we would have for a battery, so see if you can remember those. And then what is that material that's called that runs in between, like that pumpkin roll for a capacitor? I'd love it if you knew that information as well as a common use for capacitors. So with that, I'll leave you to click the link and go to the simulation page where you can play around with some of those values for the area, surface area, and the distance between the two metals to see that relationship of the charge for the voltage of a capacitor increasing or decreasing dependent upon its use. And just leave you to say, hope that you have fun and stay safe. Bye.